So for this last lecture, I'm going to be going over 4 specific techniques that you might run into in applied settings and also in academic or theoretical research. And the goal really here is to kind of give you an idea of just some of the other options that are out there. So the first thing I want to do is to reassure you that you've actually learned a lot about advanced statistics at a graduate level. A lot of graduate programs only have a single class, and sometimes it's optional. So the fact that we actually require you to take a full year of advanced statistical analysis is a marketable thing that you should be proud of. Also, the way the class is set up, we're kind of building around the most commonly used tools, and for the most part, we've been using basically beyond the t-test, multiple regression, ANOVA, and MANOVA, and techniques that basically are very similar to those. And that's for a couple of reasons. One, to make it clearer and easier to understand as we're building on techniques that are very similar to each other and use similar concepts and have similar purposes, and also to give you more tools that are more likely to be used in an applied setting. That doesn't mean that we've covered all of the world of advanced statistical analysis. In fact, there's a lot of different techniques and specialized techniques that may not necessarily directly come from multiple regression, or are looking at things very differently. And that's what we're going to kind of at least do a tour of in this lecture series. We're going to look at 4 of those techniques and when you would use them and how to kind of at least have a basic understanding of how to interpret them. I like to also refer to these lectures as mini 5 to 10 slide lectures that really should be an entire class unto themselves. If you were really learning about some of these techniques, for example, meta-analysis, I took 2 classes in as a graduate student. So I have 6 credit hours, an entire semester, or actually 2 semesters, completely devoted to understanding how to actually conduct a meta-analysis. Structural equation modeling, I actually have 3 credit hours worth of. So again, not 3 classes, 9 total credit hours. So there's a lot more that you would learn if you actually were getting, for example, a PhD in statistical analysis, and there's definitely people that have far more training than I do. I specialized in statistical analysis and industrial organizational psychology when I was in graduate school, so I sought out all of these additional classes. And my goal here is not to make you a master of any of these. My goal is to make you at least a general practitioner of multiple regression, MANOVA, and ANOVA, and hopefully I've done that. This is more of just, again, kind of enough information to know what you don't know and to be able to at least make some intelligent decisions if you run across these techniques, or at least give you a starting point if you find yourself in a situation where you would need one of these techniques in an applied setting, depending where your career takes you. So I'm going to start with the intra-class correlation. And before we even move beyond this first slide, I want to make the note of intra means internal. Most of the analyses that we've been talking about in this class have been inter. So I-N-T-E-R, not I-N-T-R-A. So inter-class correlations, where we're actually looking for the differences between classes. An intra-class correlation is actually looking to see if the similarity within groups is more important than the difference between groups. So it's actually focusing, it's kind of, think about it one way, is it kind of serves as a meeting point between, for example, principal component analysis or factor analysis and correlation or multiple regression. And there's a couple of things that we can specifically do with inter-class correlations which come up in implied settings. So we're going to talk about using them for nested designs. And this is actually a technique where we're using intra-class correlations to check some assumptions before we actually start making group comparisons. In other words, we want to ask, is the similarity within the groups important enough that we can look at the differences between the groups? Or is the differences between the groups what's more important? And we're going to find that to be useful in some applied settings. The next thing we're going to look at is you can also use intra-class correlations in theoretical settings for hypothesis testing. So an ICC versus a Pearson's R. So Pearson's R measures inter-class correlations. So variables are different classes. They might measure different constructs, for example. So IQ versus GPA, height versus weight, celebrity popularity versus number of marriages, all of which, by the way, have some form of significant correlation. However, what we're looking at in this case is the differences between groups. ICCs measure intra-class correlations within the class. So the variables are different measurements of the same thing. So in this case, what we're actually measuring, we're not actually expecting it to be correlated with each other. We're expecting it to be something that's different between groups. So kind of think about this in the form of an ANOVA. If we had an ANOVA, we would have a single DV, a single dependent variable that is continuous. That's what we're measuring. That's the construct. And we're then looking for the differences between various groups. Inter-class correlation asks a slightly different question. Based on the measurement of that DV, how is variance partialed within each class or condition compared to the differences between? So this could be a situation where we have repeated measures on the same participants, so we're basically just looking for reliability, or it could be measures of multiple people within the same group, for example, students in a classroom. So one of the reasons we would use an ICC, and like I said, this is not hypothesis testing, this is actually testing to see what's going on with the variance before maybe making other conclusions, is let's say we were doing an actual applied project where we have measurements of test performance, but those measurements are coming from 3 different groups of students. So we weren't able to use random assignment. We're basically having to use existing classrooms to look at the effect of different interventions. So before we actually ask, do the interventions differ from group to group to group, we could run an ICC to basically claim the students in these 3 different classrooms who are being exposed to 3 different conditions are relatively the same within each condition. In other words, the students are similar in group 1, group 2, and group 3 because of the ICC. And then because of that, we can make a better inference that if the differences are found because of the intervention, that's what's causing those differences. So ICCs can be used as kind of a check when you don't have random assignment to look for, and effectively what you're wanting to find is that the groups themselves are highly correlated with each other before you actually look at the differences between them. In other words, they're more similar to each other and within each class than the differences would necessarily indicate. So inter-class correlation is a statistic that measures how similar participants are within groups. So it's looking at within each cluster or each stacked group or each condition, are we finding similar variance? Are we finding similar top and bottom performance? It is a percentage of variance contributed by the unit of assignment, the level of analysis, which is usually groups of people, and we want this small for inferences about individuals. In other words, if we're using ICC to basically look to see, can we make inferences about a pre-existing condition, in other words, not random assignment, but school 1 versus school 2 versus school 3, we could run an intra-class correlation initially to try to make an argument that these schools were fairly similar to begin with. And again, the equation is very similar to everything else we've been talking about. It's means of squares of each group divided by means of squares of each group plus all other variance, and that creates an F-test, which we actually look for significance. But when we actually look at what we get when we run an intra-class correlation, there's 2 things we're interested in. We're interested in, is there significant differences within and between the groups, but we're also interested in how the groups are correlated or not correlated with each other. So the larger the ICC suggests that the subjects are more similar within the nested groups than between them. So students are different depending on the school. So the larger the ICC is, if we're using it in an applied setting, in other words, we're using it as a test to determine, can we make a stronger argument for causation without random assignment, we want a small ICC. We don't want it to be very large. Because the larger it is, the more it suggests that students are different depending on their condition of assignment, schools or classrooms. And this is generally not good, especially if we find that the ICC exceeds the treatment effect. So if the difference within each group is actually different enough that it is stronger than any treatment effect, that strongly argues that the treatment effect we found is not a treatment effect by itself. It is simply another reflection of the fact that these groups were different than to begin with. At that point, we can only make conclusions at the school level rather than the individual level, and we might want to drop treatments and examine the nested factors as a fixed factor rather than a random factor. So again, this gets at, we may need to do a different analysis at this point, and we also have less argument for us to be able to make causal conclusions. So we can also define differences between the groups. Results indicate congruence between some groups and not others. And this is how we'll often look at intra-class correlations if we're talking about hypothesis testing. Most commonly, this is done in stereotype research, where we're basically wanting to show that there's a strong congruence in how stereotypes are being recognized between different defined groups, and that's what I'm going to go over next. So this is moving from intra-class correlation as simply a way to test if non-random assignment is trustable, or is at least a better argument that there's a treatment effect when we had non-random assignment in an applied setting, and moving on to using intra-class correlations for actual statistical analysis in a more theoretical or academic way. So looking at that, this is an example of actually a fairly strong inter-item correlation matrix. So let's go at the very bottom of the equation right now. You'll notice that class is actually not significant. In fact, it's very small. That actually means that the differences between the different classes is actually fairly small at that point. So what this actually represents is that if you were actually comparing class A to class B to class C, in other words, this is the effect size of class, it's not strong. The intercept is actually what represents the intra-class correlation in this case, and it actually is significant and very strong. And what we find by looking at the inter-item correlation matrix at the top is what this was comparing at was the outcome was perceptions of stereotypes. And the stereotypes people were asked about was they were asked to think about younger people in general and then fill out a bunch of questionnaires, continuous scales, on the stereotypes they had of younger people. Those same scales of stereotype perception were then also filled out by people that were told they were supposed to think of a successful person. And those same scales were filled out by people that were told they should be thinking of an older person. Now notice that we have basically three stereotypes. The stereotypes of those that are successful, the stereotypes of those that are younger, and the stereotypes of those that are older. And in all three cases, the stereotypes are measured with ratings of the same stereotypical terms. So for instance, you might be asked, how representational is go-getting with a successful person versus a younger person versus an older person? So the actual differences in the ratings of those patterns of behavior, of those patterns of outcomes, of the perceptions of the stereotype, if we simply calculated the means, what that class result is, and that's the third line in the bottom table, is that there really is almost no difference. So the mean difference in stereotype perception of successful younger and older people is almost non-existent. However, if we actually look at the intra-class correlation, the intercept, we actually find that there's a fairly strong pattern there, that the pattern of successful younger and older are different. Not different in their means, but different in their patterns and similar in their patterns. And specifically, if we look at successful people versus younger people, a very mild correlation. If we look at successful people versus older people, a very strong correlation. So again, what this is showing is that the correlations within successful people are highly related to the correlations within older people, ratings of their stereotypes, but not related to younger people. And the relationship between younger people and older people is also not very strong. It's a very weak correlation. So taking this in combination, we use intra-class correlations, at least academically, usually to look at not are there differences between the groups on a mean of an outcome, but is there similarities and differences between groups in the patterns of how they responded to a series of questions. And again, this is a fairly complex statistical technique that can be used in multiple ways. There's a lot more to it that you have to know to really interpret interclass correlations than just these three tables. These three tables are trying to just give you a general understanding that when you're reading an article, if they start talking about ICC, you first want to ask, okay, are they using it to kind of try to bolster up or make a stronger argument for causation in a non-random practice-based setting? If so, the question you're going to be asking yourself is, did they show that basically the difference between the groups was much stronger than the similarity within the groups? That's what they're trying to accomplish, and that's what you're looking for. If they're using ICC to make a strong argument that the similarities within specific groups are highly correlated or not correlated with the similarities within other groups, then you're looking for, again, a strong ICC. So in applied setting, you're actually wanting an insignificant or a weak ICC. You're going to see none of the groups correlating very strongly. That argues that there actually is a fair amount of variance left for the effect size to describe. If you actually were using this data, for instance, to make an argument that you had an argument for practical application, so this was being used in to suggest that you could generalize these three groups, the successful group, the younger group, and the older group, this would actually argue against it. There's a very strong interclass correlation. Some of them are highly related, some of them are not, and that's not necessarily based on the effect of the difference between successful, younger, and older. However, if you're trying to make an argument theoretically, this is what you're looking for. You're looking for strong interclass correlations.